So, hi everyone, myself Ayush Tandon, and today in this video I'm gonna discuss a question from the book Concept of Physics by H.C. Verma sir. So, the question is from the chapter Photoelectric Effect, and the question says that we are given a sphere of radius r and a light of intensity I is incident on this. So, we have to find the force exerted by the light incident on the sphere if sphere is completely absorbing, and in the second part if the sphere is completely reflecting. So let us find out the force exerted by the light in these both situations. So for the first part, when the sphere is completely absorbing, the final momentum of the light would be zero. If we talk about the initial momentum, so the initial momentum can be written as energy divided by the speed of light. We can dimensionally check that it is correct. Uh, and the speed would be of the speed of the light, definitely, because the light is incident on this, and light travels with the speed of light of equal to 3 into 10 to the power 8 meters per second. So energy can be written as intensity into area. So the area uh, on which this light falls is basically pi r square. So initial momentum would be equal to I into pi r square by c, which I have written here. Now the force on this can be written as minus change in momentum divided by the time. So why minus? Because this is the momentum of the light incident. Now we have to, this light will exert how much force, that will be negative, because from the third law of motion to that force on body A by B is negative of the force by body B on body A. So that's why we have to find the momentum is for of the light. So we have to find out the force on the sphere. So it will be negative change in momentum, rate of change of momentum. So on calculating, we get the force exerted in this situation when the sphere is completely absorbing is I into pi r square by c. Now this is done. Now for the second part, if we come up here, when the sphere is completely reflecting, so there are two methods to solve this question. That is, one, by the first we take a small part and then on the sphere df part, and then we find out force on that df, and then we integrate it for the whole sphere. And the second part is to think logically. So we can't think logically like this. If you can, do tell me what you think. But let us first use calculus and integrate and then find out, and then let's see what the answer comes, and we will think if we can find out any logical approach to solve this question of reflecting. Now, while reflecting is a bit difficult, because the final momentum won't be zero. The final momentum is not zero. So as a result, we have to integrate and find out. And it is not uniform everywhere, because the area vector is at different angles. So that's why we have to integrate. We have to understand why we have to integrate and why cannot we directly find out. Now the sphere is completely reflecting. So what I did here is that first of all, I took a ring, or you can say it's a disc basically, because it's a sphere. So I've taken a disc at an angle theta from the center, and the radius would be r sin theta of this uh, sphere, right? And what I'll do next um is that I'll take a part of this on the surface of this sphere. So I've taken dA part on this uh, sphere, because light is incident on the outer part and does not penetrate inside, so it is completely reflecting. Now if we see this, so what is capital I small I and capital I small r, this and this. So this represents the initial light incident, and this is the intensity of the final. Both are same, but I have just shown that so you can get an idea of what I am trying to represent here. Now the light will follow, since that it is completely reflecting. The sphere is like a, a mirror ball, so it will follow all laws of reflection. So if the intensity of, if a light ray makes an angle theta with the dA vector, so it will get reflected at an angle theta uh, with respect to the dA vector. So dA vector here is the normal. So dA vector acts as a normal here. Now here we can write dA as pi r plus dr whole square minus pi r square. I have not written this, but I have directly written as dA can be written as 2 pi r sine theta into dr. Dr can be written as r d theta. Now you can find out this, and dr is very small, so you can ignore the dr whole square term, and you will end up at this result. This is the dA area of the sphere. Now I've taken, since I have to deal here vectorly and solve it vectorly, so I have used this sign convention, that I have taken this side as I cap and this side as j cap. Okay, now what I'll do is, of this I small initial light incident ray, I'll take the projection of this along this normal vector, along this dA vector, which will be I cos theta into dA. I have also so this is I cos theta into dA. This is the energy and this is the speed of light. And then if I resolve this thing along this normal into this coordinate system which are given here, so here if we apply, so it will be one component will be downwards and one component will be towards the right. So it will be one along I cap and one along the j cap. So it can be written as cos theta I cap plus sin theta j cap. Now the final, if we write the final momentum of the light, so again we'll take the projection of this along the dA vector, which is I cos theta into the areas dA by c, and now we will resolve this momentum into this coordinate system again. So if we see, this will be outward, away from the center. So if we resolve it, it will be along, components will be along negative I cap and negative j cap. One will be towards left and one will be towards right. So if we follow this convention, it will be where it is minus cos theta I cap minus sin theta j cap. Now there is also one thing you need to understand, where it is, yeah. So here, focus on the right part here. If we see this figure, so we are saying that dF force is acting like this towards the center, and if I take another dA part at the same angle theta, dF force will be acting towards the center, right? Now if we will take the component of this, so the net would be towards right and the vertical components will cancel each other. So vertical components will cancel each other. We can write df similarly like we wrote here, like minus delta p by delta t, but here we write the force, because here why df, because we are considering the force on a dA part, and we have not yet integrated. So it is minus delta p by delta t, which is the pi minus pf upon delta t. Now here these, by I will take delta t to be 1 second, or you can say that this is a momentum per unit time. So then delta t would automatically become 1 second. Now from these two observations, if you observe the force, this momentum and this momentum, sorry, not force, momentum, pi is equal to the negative of pf. If we take out the negative sign from here, so pi is negative of pf. So when, if we substitute this here, so we will get df is equal to 2 pi by delta t. And now we have to write 2 pi by delta. So this is 2 I cos theta dA by c cos theta I cap plus sin theta j cap. And it is correct because I chose a sign convention like this. So the force, the dA force is towards the center, and that's why I have here also drawn it towards the center. So for this part, if I take dA vector along the other side, dA area, and dF, and I see the dF force, so in this both forces, the vertical components are cancelling and the horizontal components towards the right are adding up, right? Now the df is this, see, df is this, right? Now let's go here. We'll go by the arrow. So df net can be written as df cos theta I cap. Why I have used a vector here? Because we are taking components along a vector direction, so we will, and the df force is also in the vector form, so we will take the horizontal component into consideration, right? So df net can be written as, I have written the value of df from here, and tightly written it here. So 4 I cos theta pi r square by c into sin theta d theta into I have written is this in the next line. This term was also there, into cos theta I cap plus sin theta j cap, and I have written this here, dot product of this with the cos theta I cap. Since, and if we just see where dot product makes sense, because then the vertical component will get nullified. Yeah, right. And because j dot I is 0 and I dot I is 1. df net can be written as 4 I cap cos, from here it's cos square, right? And there two, and there is 3 cos terms, so 4 I cos cube theta sin theta d theta, and this constant which is pi r square by c. Now let's take the constants on one side, and now the only task we have to do is to integrate this force for theta, because at an angle theta we have taken d theta. I have not represented that d theta, it's my mistake. uh, at an angle theta and then d theta, because that's why. Okay, yeah, I should have shown that here, that at an angle theta we have taken d theta area of that width. Yeah, correct. Yeah. So now if we integrate this force, which is 4, and we have taken out the constant which is 4 I pi r square by c, integral of cos cube theta sin theta d theta, this is sin theta, not sin 0. And the integration would be from 0 to pi by 2. Yeah, see, correct, it's correct. Integration is from 0 to pi by 2. Hold on. Yeah, in this you can see 0 to pi by 2. So now this is, it's just integration. You can, there are two methods to solve. You can substitute cos theta as t and then sin theta, then d, you can just use substitution, and I have directly written it like this, that derivative of cos theta is minus sin theta. I have supplied a negative sign, so sin theta can be written as minus of derivative of cos theta. So you can assume that cos theta is some x, cos cube theta is x cube, so it will be, oh wait, uh, it will be cos cube, and it's not to be d theta, it will be theta, that's a mistake. Yeah, so it is cos cube theta into d of cos theta, right? And if we integrate it, it's a simple integration like t cube dt, which is t to the power 4 upon 4 plus c. So this is the integration, cos minus cos to the power 4, cos theta to the power 4 upon 4, and then we'll just apply the limits from 0 to pi by 2, and bingo, we have found out the force. Force is I pi r square by c. We have calculated this force when the sphere is completely reflecting. Now there's one thing to observe. We see the force when the sphere is completely absorbing was also I pi r square by c, right? Now, and when the sphere is completely reflecting, it is again pi r square by c. So f is same if sphere is completely absorbing or completely reflecting. Now why? How can we justify this also without using so much maths or without taking so much calculus? Let us see, and let us go now on the logical approach of this question. See, when, if the light is incident at an angle theta equal to 45 degree, so the light will be reflected perpendicularly upwards. See, you can follow the laws of reflection. If it is incident at an angle of 45 degrees, see, if I have taken a special angle 45 degrees, and after this all the light is going perpendicularly upwards. Now I'll take two cases here, that the light incident at an angles below 45 and light incident at an angles above 45 degree. Now here I've taken theta is less than 45 degree. So if the theta is less than 45 degree, it will be reflected in this plane backwards. It will be reflected backwards in the direction, like if the light is was incident in I cap, so it will be reflected in I cap minus I cap with some components. I don't care, but it will be basically it will be reflected backwards. And if the angles are greater, if it is incident at an angle greater than 45 degree, so this will deviate like this. So at bigger angles, so it will be, they will have a component in I cap only. And if you see both, so there some light is deviating backwards, some light is deviating in front. It is just like you can understand in the Rutherford model, like so most of the one light is deviating backwards, and most of the light deviated at larger angles, and some deviated at back. So if you just see the Rutherford model, it is something situation something like this. So they cancel effect of each other, and we can, by this logic we can say that the force would be same, the final momentum would be zero, the final momentum would be zero, right? Here at this is like here the direction of reflection and here are both opposite, so they will cancel each other, and we can say the final momentum would be zero in this case also. So the force would be equal to I into pi r square by c. So it's just like the situation of completely absorbing, right? So this was the how you can think without solving this. Okay, so let me show you the solution once again, right? Okay, so this was the question. This was a very interesting question, and thank you.